Okay, so we figured out what momentum was. It's just the product of mass and velocity, or how hard something is going to hit you, right? And it depends upon both mass and velocity. It's a vector, and that means, you will have to resolve it. If you want, you will have to resolve it into components. If you have an angled momentum, if you want to find out the change in momentum, for example, right, you can simply just use the final momentum minus initial momentum formula, right? Final minus initial. So make sure you're careful with the signs because they're a vector quantity. Okay, now question: how is it that Newton's second law is related to momentum? Okay, I'm going to give you an example. Okay, let's say, does any of you watch cricket? Yes. Anyone likes cricket? Pakistani cricket? I don't, but a lot of my students do. Yes. Does anyone know Shahid Afridi? If you do, then that's great. Well, everyone knows him, regardless of whether they watch cricket or not. Okay, let's say that you've got a ball of a kilogram, it's pretty heavy, and Shaheen threw a ball at 40 meters per second velocity. And Shahid Afridi was pretty determined to hit a sixer in from his bat. Okay. Then Shahid Afridi hit the ball and the ball went flying with 80 meters per second. Okay. So obviously Shahid Afridi applied a certain force, right? And we know that the time of the contact with the bat was actually 0.2 seconds. Okay. The question arises, by how much force did Shahid Afridi hit the ball? Anyone would like to try? Yes, Ariz. Any idea? How can you figure out the force applied by Shahid? How do you figure out the force that Shahid Afridi hit it by? No? Yes, Ariz. Can you hear me? Any idea? Nope.
Yeah, I can hear you. Yeah.
Hmm. Should I do it? Anyone else would like to try? Force. Yes, Anya. Any idea?
First we're gonna find like the change in momentum for this.
That's great. Excellent. So we earlier just figured out that resultant force is actually change in momentum over change in time. Absolutely. So if I just know what the change in momentum of the ball is and I divide it by the time of contact, that'll give me the resultant force, right? Okay. But rather than getting to this formula directly, how about we start off with the formula that you know? F is equals to ma, right? Now the problem over here is I know the mass of the ball, where it was 1 kg, right? But I don't know what the acceleration was. But isn't acceleration just equal to v minus u divided by t, right? So you can do it this way as well. So 1 multiplied by what was the final velocity? The final velocity, make sure you're careful of the signs. So if you're using this as, let's say, for example, let's choose the right side as negative and the left side as positive. You can choose whatever you want, but make sure you change the signs then. Okay. So what is final velocity? That's 80. Okay. Minus what is the initial velocity? That's just minus 40, right? And what was the time taken? That was 0.2 seconds. And there you have it. Resultant force is equals to 80 plus 40. So 120 divided by 0.2. So that's 600 newtons. 600 newtons is the force applied by Shahid Afridi. So do you see how resultant force can be used according to this formula? Or you could do it the other way as well. You could also do it by the formula Fr is equals to change in momentum divided by change in time. Now, what is the change in momentum? Change in momentum is just mv minus mu divided by t, right? And what is mv? That's just 80 times 1 minus what is the initial momentum? We chose that as negative. So that's just minus 40 times 1 divided by 0.2. And again, you've still gotten your resultant force as 600 newtons. Okay, so that's how you can get this. And now, how are these formulas related? Now I'm going to derive it for you. Very, very important. How do I get Fr is equals to delta P over delta T? It's pretty easy. You know that, for example, Fr is equals to ma, right? You can do it either ways. You can start from ma or you can start from delta P over delta T. Now, isn't acceleration equal to v minus u over t? And if you were to multiply it, if you were to multiply m, wouldn't you get mv minus mu divided by t, right? And isn't if you take m as common, right, you just come back to the same formula, right? But isn't mv just final momentum minus initial momentum divided by time, because mv is final momentum and mu is initial momentum. And what does this turn out to? Isn't that just change in momentum over change in time, right? So fr is equals to ma, or fr is equals to change in momentum over change in time. Okay, so that's how you were to write this formula. So this is Newton's second law, right? This is Newton's second law. This is a result of Newton's second law. This is application of Newton's second law, or it's kind of like an extension of Newton's second law, and it's more applicable in most cases, but this covers absolutely everything. This covers absolutely everything. Make sense? Up to this point,
But
should I move on? Yes.
you said it's delta P by delta T, yeah, for the force.
Hmm.
Then over
Uh,
here, they just gave us the point of contact as 0.2. Like, what if they gave us like the time for both of the balls to
uh,
contact with the bat? Then
what do you
would
mean?
we have to like in
S-
what case do we have to do the delta like
So the
like
delta is
like,
always there. The delta is always there. So in this case, I could write delta as well. I could write delta here as well. Delta here as well is the same thing. So why we write delta t as more, you could say, appropriate is because I have already given you the time of contact. Okay. What I could also do was that, for example, the ball reached at this point at 0.1 seconds. Okay. And the ball left at this point at 0. Let's say 3 seconds. Okay. Now you will, if you want to use t in your equation, you will neither use 0.1, you will neither use 0.3. You will take delta t, right? What was the time that the ball was in contact with the bat? Okay, so that's why we use delta t, which is more precise. And even if you remember, I have not taught acceleration as v minus u over t. Like, that is okay, but an even better formula would be delta v over delta t. So the change in both of them. So this is more accurate. But generally, this also works in pretty simple cases. Okay.
all right.
Okay. Now, makes sense? So this is just delta P over delta T. We're going to be using delta P over delta T pretty soon as well. But first, let's solve a few difficult questions for F is equals to MA. Now, F is equals to MA seems pretty easy to use, but it gets slightly complicated, when you're doing different questions. So, for example, what is it? Okay. We'll come back to, delta P over delta T in a bit. But first, let's master MA, because that's the one that you're already familiar with. Question says, a box of mass 8 kilograms rests on a frictionless surface, which is attached to a pulley connected to a smaller 2 kilogram mass. Okay. So they're connected by a wire. And what is the acceleration of the 8 kilogram box? Question. So basically, this question is organized in such a way that you have to figure out that what is the acceleration of the entire system, right? What's going to happen is this box is connected to this box, right? This box is going to fall down. And when this box is falling down, it's going to pull away this box with itself. Okay. But how do I find out the acceleration? What do I do? Think about it. Think for a minute. And if you have any answers, you can tell me. Try it. Suggest what should we do. It's okay if we got it wrong. The entire point is to get it as wrong as possible so that we can do it right. And I am going to pick up the pace, right? I already told you that before. If you do not tell me that I have a problem with this, I will move on rather than, if I ask you every single time. So if you do not get something, just stop me right there and I'll explain it to you then. Okay. Yes. What do you think, Anya? How do I solve it?
No, I don't get it because like only the mass is given. So
Hmm. The mass is given, absolutely. What do you think, Kaima? Any ideas how to solve this question? This is a past paper question, by the way. This came in the, I don't know which year, but this was a question from the MCQ paper. Yes.
Why are the MCQs always so hard?
Yeah, the MCQs are hard, absolutely. The MCQs are hard not because the working they require, but because you're lost where to look. In paper two, they always just guide you. Okay, go here, then find this. In MCQs, you're just on your own. Yes, Kaima, any ideas?
no.
Hmm. Okay. We have to use the formula FR is equals to MA. Keep in mind, this is a resultant force. Okay. Now, the problem is I have to find out the acceleration, which is equals to which is equals to FR divided by the mass, right? This is how you find out acceleration using this formula. Now, I do have, I don't have anything like, I don't know what the resultant force is, and I don't know what the mass is. Okay. Now, how do I solve this? First of all, what is the driving force of the system? What is actually pulling you down? It's this box, right? This box is just resting on its own, right? This box is not doing anything. So, what is pulling this force down? It's the weight, right? Do we know what the weight of the box is? Yes, we do. It's 2 times 9.81. So that means there is one driving force, which is 19.6 newtons, right? This is the driving force. If this box was not hanging on the, from the edge, there would be no force that's pulling anyone down. This is the driving force. So this is the driving force. Okay. Is there any other force on the entire system? No, there isn't, right? This is the only thing that's pulling the entire thing down. They're connected. Okay. Now, what is the resultant force? That's just 19.6 Newton because there is no other force that's moving you, right? Now, what is the mass? What do I take as the mass? Do I take it as 2 kilograms or do I take it as 8? Yes, Aris, what do you think? Do I take the mass as 2 or 8?
I think too.
2, okay. Hania, what do you think?
8.
8. Kaima, what do you think? Should I take it as 2 and 8 or 8? What do I take as the mass over here? I have figured out this. What are you saying?
Do you take both?
Hmm. It's possible. It's possible. In fact, that's right. You're right, Kaima. You are going to take 8 plus 2 both. So that means it's going to be 19.6 Newton divided by 10, which is equals to 1.96 meters per second square. This is the acceleration. Now, why did I take both? Because the 19.6 Newton force is driving both 8 kg and 2 kg masses, right? Check it out. The 19.6 force is not just moving the 2 kilogram box, right? If this was not over there, okay, then that's absolutely what you would do. You would just do 19.6 divided by 2, right? 19.6 divided by 2, and that would just give you 9.6, oh, sorry, 9.81, right? That's just exactly what you would get. But now you see that the 2 kilogram box is actually connected to the 8 kilogram box. This is not applying any other force, right? This is not hanging from the edge, right? So you could assume that this has no weight at the moment. It's just, lying there. That means the 2 kilogram box, the weight has to pull not just 2 kilograms, but 8 kilograms with itself as well. So that's why you're going to take both the masses, 10 kgs. Okay. Now, what if this was the scenario? Okay. Now, I've switched around the boxes. Acceleration. What is the acceleration now? Okay. First of all, if I want to figure out the by the way, keep in mind, both will have the same acceleration. If they're connected, they will both have the same acceleration, right? For example, like a train. If the train is moving together, so that means all the compartments of the train have the same velocity and the same acceleration. All have same acceleration, or they would not be moving together. Okay. Now, again, do you see that now, if you want to find out the acceleration, this is going to accelerate like this, and this is going to accelerate like this. Now, What is the driving force? A resultant force is equals to ma. What is the acceleration? It's just equal to Fr divided by mass. Resultant force. Ding, ding, ding. What is the resultant force? There is only one driving force in the entire system. It is this, the weight of this box, because it's hanging, and that means it's going to pull everything along itself. What is the weight? 8 into 9.81. That is 78.48 newtons. Okay, I figured out what the resultant force is. This is the driving force. This is the driving force. There is no other force that is in the system at the moment. Okay, resultant force, I found it, 78.48 Newton. What should be the total mass now? What should what should I divide mass by? Would it be 8 or 2 or both? Asania, what do you think now?
It would be both.
It would be both. Exactly. And you see that now the acceleration is going to be 7.84 ms minus 2. Now, what is different in both of these scenarios? In this case, like I've kept the same both boxes. I only switched their directions, their positions. In this case, it was the 2 kilogram box which was pulling everything down. But now it's the 8 kilogram box that is pulling everything down. So clearly, because the 8 kilogram the 8 kilogram weight provides a greater driving force, that's why the acceleration of the entire system is greater. Okay. Got it? Yes. 8 plus 2.
Yeah.
Hmm. Okay. Moving on. This question is for you. Question says, a train of mass 80,000 kilograms is at rest at a station. Okay. It carries 400 passengers, each with an average mass of 70 kgs. The train starts moving when a constant force of 250,000 newtons applied. There is no friction or air resistance. Calculate the acceleration of the train once it starts moving. It's a good question. Try solving it. You have 2 minutes. It's a pretty simple example. You just have to use the formula. Yes, done.
Yeah, I'm done with the first one.
Okay. Okay. Yes, Hania, done. Kaima, question number 1 done. Aris, what was your answer?
I got 3.019.
3.019. Hania, what did you get?
I got 2.31.
2.31. Kaima, what did you get?
I also got 2.31.
2.31. Okay, let's check which one is right now. It's either it's 2v1 or is let's check. A train of mass 80,000 kilograms is at rest at a station. It carries 400 passengers, each with an average mass of 70 kg. Okay, let's draw the train. So the train has a mass of 80,000 kilogram and it has 400 passengers. So their total mass is 400 multiplied by 70 kilograms. Okay. And it says that the train is pushing with a constant force of 250,000 Newton. Okay. And it says calculate the acceleration of the block, sorry, of the engine. Okay. Now, problem. Fr is equals to ma. Acceleration is equals to resultant force divided by mass. What is the resultant force? That's absolutely 250,000. But what is the mass? What is the mass? What is the mass? Do I take it as 80,000? Do I take it as 400 into 70 or do I add them? Let's check. First of all, you have to realize that this force is not just pulling the train, it's pulling the people in it as well. Because if the train was applying this force without the people in it, the train would absolutely have a greater acceleration because it's pulling a lighter mass. But because of the people, you have to add in the people as well because this force accelerates both train as well as the people, train plus people, right? So I have to take the total mass of the train as well as the people. So 80,000 plus what was the mass of the people? 400 into 70. 400 into 70. And I have the answer, whatever that answer is. What is the answer? Is that what you wrote, Anya? Or was yours different?
No, it was the same.
It was the same. So 80,000 plus 400 into 70. Yep, that's right. That comes out 2.31 meters per second square. Okay. See, yes, Aris, what did you do?
I multiplied 400 by 7 by mistake.
You have to include the train as well because the train is the one that's moving, right? You've got to include the mass of the train and the people. Make sense?
No, I did
Hmm.
the same thing. Only thing is that, like, by mistake,
Hmm.
I instead of
Oh,
400 into 70, I did 7.
okay. Did you got the problem? You got the
Yeah, I
okay,
understood what I did wrong
okay,
the
okay,
moment I just
okay.
rechecked.
So sounds good. Question. Next question. If an engine applies a constant force of 5,000 newtons, but there is friction of 1,500 newtons, okay, think it through. Find the velocity of the car after 5 seconds. If the car starts from rest, this is worth 3 marks. You may start solving. What do you think? I will solve it in 2 minutes. You just have to use the formula. It's pretty easy. Yes, has anyone figured it out yet? It's pretty easy. Just have to plug in values. Yes, Aris, did you get an answer?
I'm still doing it. I'm on the
Hmm.
working.
Okay, okay. Yes, Anya, you done? Kaima?
Yeah, I got 11.67.
167. Okay. We'll check it. Yes, Kaima, did you get an answer?
I'm still not done.
Hmm. Okay. I am going to start solving it now. So you just have to use the formula again. FR is equals to MA, right? Keep in mind that this is a resultant force, right? Resultant force means the net force. So if you're using this formula, make sure you're using the net force. If you use 5,000, that's wrong. If you use 1,500, that's wrong. If you use 5,000 plus 1,500, that's also wrong because this is in the opposite direction. So you're going to do what? 5,000 minus 1,500, okay, is equals to MA. We already know what M is, 1,500. What is A? We don't know. And we want to find out the velocity. So what if instead of A, we wrote V minus U divided by T? Isn't that also right? Okay. So this just becomes what? This just becomes 3,500. 3,500 newtons. And what is V? That's what we want to find out. So 500 into V, and U is 0. How do I know that U is 0? Because it starts from rest. It is starting from rest. Okay. So V is unknown. And what is the time? I'm talking about the time that it takes. We want to find out the velocity of the car after 5 seconds. So we already have been given the time as well. So you plug in time over here, which is 5, 3,500 over here. Now, it's just multiplication. 3,500 multiplied by 5 divided by 1,500. And there you have it. You have velocity. 3,500 into 5 divided by 1,500. So 11.66. That's absolutely right. Great, Hanya. Meters per second. And there you have it. Any problems? Yes. Kaima, did you get it? Just put in some numbers and crunched it.
Yeah, I got the same answer as well.
Okay. Sounds good. Yes, Anya, shall we move on? Oh, sorry. Kaima, shall we move on? Or no?
Can you please give me a second? I'm still
Okay.
looking at it.
Okay, okay.
Yeah, you can move on. So you can move on now.
Okay. Okay, let's move on. Now what we're going to do is now we're going to be doing a paper 3 type experiment, although on paper. Okay. We're going to be designing an experiment to prove Newton's second law. Okay. And basically what they want us to do is they want us to investigate a relationship between force, mass, and acceleration. Can you prove Newton's second law by using an apparatus? Can you design an experiment? We absolutely can. We can with a pulley, right? But why do we need a pulley? First of all, so I'm going to describe the experiment to you in a minute. So let me tell you what we're going to do. We're going to prove Newton's second law by just using like a pulley and a cart. F is equals to ma. We want to do this. By the way, this is what we call a pulley. That's, a wheel that turns around. Okay. How do I prove this? First of all, according to Newton's second law, Fr is equals to ma. We want to experimentally prove it. This tells us that resultant force is directly proportional to mass. If I increase the mass, resultant force should increase. I need a greater force to push greater masses. And if the mass is inversely proportional to acceleration, that means if the mass is greater and if I apply the same force, it will accelerate less. Okay, so these are the two, you could say, deductions of Newton's second law. Keep in mind that when I say that resultant force is directly proportional to mass, I am saying that acceleration is constant. Whenever you say that I want to see the relationship between two things, you have to assume everything else is constant. So if I'm saying that when I increase the mass, it requires a greater resultant force, I have to assume that acceleration is constant, right? In order to make this deduction, I have to say that everything else is constant. And then if everything else is constant, only then when I increase the mass, the resultant force required is greater. Okay. In the same way, if mass is inversely proportional to acceleration, that means that when I increase the mass, it accelerates less. The assumption over here is that the force is constant. That means if I apply the same force to a smaller mass and the same force to a greater mass, the one with the greater mass will accelerate less. So this is what it's telling me. So whenever you want to deduce or whenever you want to investigate a relationship between two variables, you keep everything else constant. The basic idea is, for example, that when you study more, your grades increase. So when you're saying that they're directly proportional, okay, you have to assume that everything else is constant, okay? Because what if the child had a really easy test and he did not study, right? So you have to assume that everyone had the same, you could say, test, okay? Then you have to assume that everything else was constant. For example, did the grades rise due to something else? Did the grades increase due to, let's say, for example, if hmm, what else could it be? For example, yes, for example, if the student was cheating, right? Even then, you would see that the child did not have to study, but his grades improved anyways, right? Although he paid a much greater cost. So in this case, when I'm saying that study is directly proportional to grades, I have to assume everything else is constant. So I can see the effect of only studying on grades. For example, a plant, right? For example, I say that sunlight is directly proportional to the height of a plant height, okay? Now, in this case, I'm saying that as I increase the sunlight, the height of a plant is going to increase. But in order to deduce this relationship, I have to assume everything else is constant. Because what if the height of the plant increased due to extra water? What if the height increased due to extra fertilizer? What if the height increased due to, nutritious soil or something, right? I have to keep everything else the same. And only then will it allow me to see the effect of just sunlight on the height of the plant. Okay. So that's what this is a really, really important, you could say, framework for practicals, for experiments. Okay. Now, the experiment, this is going to be really helpful for you in paper 3 as well, the practical paper. We're not doing the practical, but it's going to develop a way of thinking about the practicals. Okay, what I'm going to do is, what do I have? I have this apparatus. Okay, so this is basically a car. Okay, and this car has, you could say, weight on it. Okay, you can put multiple plates of weight on it, and this car is connected. This is a you could say it's a floor, it's a track, and this car can run on this track, and it's connected by a wire, and this wire is connected downwards to a hanging weight. Okay, now this hanging weight, you can apply, you could say, play onto it. I'm going to send you a video of this as well. So what's going to happen is basically the same we just did. We just determined this is the trolley and this is the weights that's hanging, right? So it's exactly the same setup over here. This is the trolley with weight and it's connected to a pulley with a hanging weight as well. Okay. So, and I have a total of 10 kilogram plates, sorry, 10 gram plates. So these are like, these are like onion rings that you can place over here and you can keep on adding as many onion rings you want. Okay. So you've got 10-gram onion rings. Okay. And you got 10 of these plates. So the total mass is what? That's 10 gram multiplied by 10. So you have a total mass of 100 grams. So like 10 gram, 10 gram, 10 gram, 10 gram, 10 gram. Okay. Part one. Let's prove part one of the experiment. Force is directly proportional to acceleration. Okay. Now, if I'm saying that, I am assuming that mass is constant. Okay. That if mass is constant, okay, only then when I apply a greater force, the acceleration increases. Or it could also be that if I reduce the force, the acceleration falls. Okay, that's also perfectly fine. If I reduce the force, it should accelerate less. But I have to assume mass is constant, because if I don't keep mass the same, then it will affect my acceleration and it will affect my force. That's why I have to keep everything else in the formula constant. Okay, same example over here. Let's see. I have got 80-gram plates over here and I've got 20-gram plates over here. Now, what is the driving force of the system? This system is going to slide like this. That means this is the only driving force, the weight of this, right? And what is the weight of this? That is just 20 gram. That's just, weight is equals to what? Mg. And what is the mass of this? It's not 20. You have to use kilograms. So that means 20 into 10 raised to power minus 3. Why did I use minus 3? Why did I use minus 3? Because I've got to use kilograms, right? 1 gram, if you want, for example, 1 kilogram is equals to 1,000 grams, right? So you could say 1 gram is equals to 1 divided by 1,000 kilograms, right? You could say that. Or you could also say that if you want to convert 1 gram to kilograms, right, you just multiply into 10 to the power minus 3. But if you want to convert kilogram to gram, you could convert into 10 raised to the power 3. I'll send you a video, a short video on YouTube that is really good with these conversions. And I would highly recommend that you watch it. It's going to help you in, whatever subjects that you have. Really, really important. Okay. So, or you could just, 20 divided by 1,000. That's also perfectly fine. So 20 into 10 raised to the power minus 3 is my mass in kilograms. Okay. Into G into 9.81. So let's check out what the weight is. 20 into 10 to the power minus 3 multiplied by 9.81. 0.1962 Newton. Now, my driving force of the entire system is a 0.1962. Okay. What is the acceleration of the system? Let's check. Fr is equals to ma. Acceleration is equals to resultant force divided by mass. What is the resultant force? That is just 0.1962, because that is the only driving force in the system. Because this mass is not hanging, it's not applying any force that's making us move or fall down. What is the mass? You take the total mass, because this little weight is pushing everything, not just this one, it's pushing everything. So that's just going to be what? That's going to be 80 plus 20 grams or 0.1 kg, right? Because 100 gram is equals to 0.1 kg. And then when you do that, you will get what? You will get 0.1962 divided by, oh, that's just going to be 10 times that. Yep, that's just going to be 1.962 ms minus 2 is the acceleration. Now keep these accelerations in mind. We're going to draw a table at the end as well. Okay. Now what do you see over here? What I'm going to do is I'm going to take two of these plates. Okay. I'm going to take two of these plates and I'm going to put them over here. Okay, so I took out plates from over here and I'm going to put them over here. So the total mass of the system remains the same, right? If you check, the trolley now has 60 grams, but now I've increased the mass that is hanging. So doesn't that mean that the weight is now going to increase because more force is falling down? Let's check. What is the weight now? What is the mass? That's 40 divided by 1,000 multiplied by 9.81. Let's check. So that is going to be double of that, right? So what was the 0.1962 multiplied by 2? So that's just 0.3924 Newton. Okay. Again, acceleration is equals to resultant force divided by mass. What is the resultant force? It's the same. Oh, sorry, the resultant force is not the same. It's higher, 0.3924 Newton. What is the mass? It's still the same. The total mass of the system is still the same. 60 plus 40 gram, 0.1 kg. 0.1 kg. And what does that give me as acceleration? 3.924 ms minus 2. Now check out the values. We experimentally proved that when I increase the resultant force, check it out. I increase the resultant force. That's it. I only change the resultant force, right? The mass of the total system is still the same. 0.1 kg over here, 0.1 kg over here. I saw that if I kept the mass of the entire system constant, due to resultant force increasing, my acceleration increases. It literally increases. You can see it in the formula. You can even prove it. You can do this experiment. You do this experiment. Well, although A levels does not really include this apparatus, but they could give you like similar setups to make you prove this, or they could give you an experimental design as well in the theoretical paper. Where they give you this example and they ask you to calculate it step by step exactly like we did, right? Yes, are you guys following me? Or am I just having fun on my own?
Yeah, I understand.
Yes, yes, Kaima. Are you getting what we did?
Yeah.
Okay. Hania, make sense?
Yeah.
Okay. Now, last thing for you. Calculate the acceleration of this one. So 80-gram plates over here and 20-gram plates over here. Calculate the acceleration for this setup. You've got 2 minutes. We will have a short break in like 8 to 9 minutes, and we will have a break of 10 minutes, and then we will continue till uh, I think 1 p.m. for you or something. Yes, Kaima, what did the acceleration come out to?
So can you please give me a second?
Okay.
So I think I got the answer.
Okay. Yes, Hania, have you gotten the answer as well?
Yeah.
What did you get, Hania?
I got 7.848.
84 ms minus 2. Yes, Aris, did you get the same?
Same.
Okay. Yes, Kaima, you should be getting this answer.
Yeah, I got it. But
Okay. Uh,
at first I
Okay.
made a mistake first, like
Okay. So acceleration is equals to resultant force divided by mass, right? Resultant force is going to be this weight that's hanging down. Mass into G. The mass is not 80 multiplied by 9.81. It's 80 divided by 1000 into 9.81, right? So you plug this over here, plug in this over here, divide by the mass. What was the mass? That was just the total system mass, 20 gram plus 80 gram, which is 0.1 kg. And then you should get this answer. Okay. Now again, check this out. The resultant force is what? Aris, what did you get as the resultant force?
Resultant force, I got 0.7848.
848. Okay. So, okay. Now check this out again. Do you see that as you increase the resultant force, the acceleration was increasing? Now, when the driving force was what? The driving force was 0.1962. My acceleration was what? 1.962. When my driving force was 0.3942, or this one, 3942, my acceleration was what? 3.942. 942. And then when my driving force was 0.784, my acceleration was 7.84. I clearly see that as my force increases, my acceleration also increases. And clearly, this has been proven. The first part of Newton's second law has been proven. Okay. The next one is what? The next one is part 2. Now, this one is going to be that how do you prove the other one? Acceleration is inversely proportional to mass. But in this case, the assumption would be what? Force is supposed to be constant. Okay. How much have we done so far? 1, 2, 3. Okay. Okay. Excellent. Sounds good. That'll be all. And let's take like a 10-minute break. Okay. And right now it's like 12:56 something at my place. And I will see you in like 10 minutes. So like 1067. Okay.
All right.
Okay. Sounds good. You may visit back this link. This link is the same one
Okay.
at
All right.
in like 10 minutes. Okay.
Yeah.
Okay. Let's resume back to what we were doing. Okay. So we first proved the original part of Newton's second law, right? F is equals to ma. We proved it. We proved that when you increase the acceleration, when you increase the force, the acceleration increases. Now, the second part of the law. We're going to prove that when mass increases, acceleration falls. But you have to keep force the same. Okay. So basically, you have to take multiple readings and you have to somehow change the apparatus, okay, so that you can get to proving this law. So basically that means that you have to take multiple values of mass and acceleration, mass and acceleration, mass and acceleration. And let's say that when you increase the mass, okay, the acceleration falls. That's exactly what you have to prove. You have to make sure that you somehow change the mass by keeping force the same. Okay. Now I'll tell you how to do that. So what you do is you have the same 10 plates. Okay. You have the same 10-gram plates, 10 of those. And you don't even need to like use all of them. Okay. First of all, what if I were to do it like this? This is the driving force. Okay, let's take 40 gram at the start and let's take 20 gram over here. This is just a starting point. You can choose whatever starting point you want. Okay, you can take this 100, you could take this 0, you could take this 80, you could take this 20, you could take this 40 and this 60, whatever you want. Okay, let's just start from here. Okay, now what would be the weight of this? What would be the driving force? That's a 0. 40 gram divided by 1000. So 40 divided by 1000 into 9.81. So that is 40 over 1000 into 9.81. So that's just 0.3924 Newton. Okay. Let's check the acceleration. Fr over m. Resultant force was what? 0.3924. Now the mass is different. The total mass of the system is different. It's not 100, right? Initially, we kept the mass the same because that was our condition. We kept the total mass of the system the same. In all of the formulas, the mass was the same. But in this scenario, the mass is different, okay? So basically, that means, what is the mass now? That's just 40 plus 20, right? So that's actually going to be 60 divided by 1000. Why? Because I want 60. This is the total mass 20 plus 40. So that's 60. Let's check it out. 0.3942 divided by 106. So 6.57 ms minus 2. This is the acceleration for the start. Okay. But now, how do I prove that when I increase the mass, acceleration falls? Then you add more mass. Now, I'm going to keep the driving force the same. Okay. I kept the driving force the same. So that means the weight is still the same. The hanging weight is still the same. It is equals to 0.3924 Newton. Okay. But now I have increased the total mass of the system. Acceleration is what? Fr over m. Resultant force is the same. I'm keeping it the same. 0.3924. And what is the mass now? It's actually 40 plus 40 divided by 1000. Right? Do you see how we literally change the mass? And now I'm going to show you how it varies. The answer comes out to 4.93 ms minus 2. Now check it out. Do you see that in these examples, acceleration is 6.57, acceleration is equals to 4.93. Now over here, you see that what I did was I kept F the same. Okay. I increased the mass, which reduced my acceleration. I literally see it happening. Okay. Now I'm going to increase the mass even more. Now I'm going to increase the weight of the trolley even more. Let's check it out. Acceleration is equals to Fr over m. What is the resultant force? It's still the same because the driving weight is still the same. 0.3924 Newton. 0.3924 divided by, what's the mass now? It's 40 plus 60. So that's 0.1 kg. 100 divided by 1000. Divide by, so 3 point, oh, what happened? 0.3942 ms minus 2. And here it is again. You see that you increase the mass again. You increase the mass again and your acceleration fell. Again, F is the same. You keep F the same because if F is not the same, then it would vary your results. So again, total mass was what? Initially, total mass was 60 gram. 60 gram. And what was your acceleration? That was 6.57. Your total mass again in the second experiment was what? 0 point what? Oh, sorry. That was 80 gram. 80 gram. And what was the acceleration? 4.93. My total mass in the final question was 100 gram. And my acceleration was what? 3.94. So I clearly see that when the mass increases, the acceleration is falling. As mass is increasing, acceleration is falling. And there you have it. Newton's second law, part 2 has also been proved. So this is a way you actually design an experiment. This is how you would actually do multiple experiments, and then you would repeat it by changing the conditions, and you would see what is the effect of changing that condition. That's how you have proved Newton's second law. Yes. Any questions? Hania, Kaima, Haris?
No,
Hmm.
but could I just read through it?
Here it
again?
is. Yep. You absolutely will have to write it after class, have a few minutes to look at it, understand it, do it yourself. Only then will you actually understand it. Yes, Hania. Any questions up till now?
No, I got it.
Okay. Yes, Kaima. Did you get it? What we're
Yeah.
trying to achieve? Okay. Kaima, do you make notes within class or later on? Or what?
I make like within, but if I miss something, I
Hmm. Okay.
like later.
Okay. Because making notes after class, between class, whatever you do are really, really important because that's how you revise. That's how you learn. You learn once in class, and then you learn later on. The greater amount of learning happens after class. Within the class, I'm only like exposing you to the content. I'm showing you this is how it is. This is how you solve a certain question. But it only gets into your brain once you're doing it after class, when you take out a few minutes and you actually try to understand what the hell did we just do? Did I really understand it? Can I solve this completely on my own from scratch? That's how you learn. If you're not doing that, you are not learning anything. Keep that in mind. Okay. Yes, Aris, should we move on?
Yeah.
Okay. Now, now we are going to return to delta P over delta T, right? Newton's second law, the general definition was what? Resultant force is equals to delta P over delta T, or or you could say is Fr is equal to rate of change of momentum. Hani, have you done like these momentum time graphs at your school?
I probably have done it, but like I don't remember.
Okay. So these are really, really important. This is like one of the most important ones in Newton's second law. F is equals to ma, that's good. That's mostly IGCSE stuff and slightly difficult questions, but this is new and you've got to pay really good attention for this. Okay. So Newton's second law said that resultant force is rate of change of momentum. Really important, okay? That means if you were to plot a momentum time graph, this is momentum on the y-axis and time on the x-axis. If you were to plot a graph, the slope of a momentum time graph is actually going to be resultant force. Resultant force. Why? Because if you were to take the slope of this, what would the slope of this be? Change in y over change in x. And what is on the y-axis? Isn't that change in momentum? And what is on the x-axis? Isn't that change in time? Doesn't that mean that the slope of this graph is just what? It's just a resultant force. So that means if you were to take the slope of a momentum time graph, that's just going to give me resultant force. So if I see that gradient is example, from here to here, from here to here, the slope was equal to 5, example 5. This means that 5 newtons was resultant force. So from this portion to this portion, okay? But what about this portion? Now from this portion, because gradient was 0, that means resultant force is also 0, right? Because if you see that the slope of the line is 0, the resultant force is also 0. Remember this. The slope of a momentum time graph is resultant force. And if it makes sense also, check it out. Newton's first law and Newton's second law says that an object will maintain its momentum until a resultant force acts on it. Do you see that momentum is constant? It keeps on moving. The only way it can maintain its momentum is if there is no resultant force acting on it. Because if the resultant force was acting on it, the graph would probably go here, or whatever. But if there's no resultant force, it's just going to keep on going straight and so on, right? That agrees with Newton's first and second law. Okay. Now check this one out. For this part, again, the slope of the momentum time graph, the gradient is the average force or the resultant force. M of momentum, this should be really, really, really ingrained into your head, is equal to resultant force. So let's check this out. So from here to here, the slope is 0. that means the resultant force is 0. There is no resultant force acting on it, right? From let's say T1 to T2. Okay. But from here onwards, T2 to T3, this has a certain slope. Let's So from T2 to T3, it has a positive slope. M is equals to positive, which means that resultant force is equals to some positive value as well. Okay. So you could describe that as, let's say, you could say that when there is an FR, momentum changes. Momentum changes from T2 to T3, right? If you to take the slope of this, how quickly your momentum changes, that should tell you the resultant force. So if you were to take the slope of this, it's going to tell you the resultant force, okay? If there is a greater slope, that would imply that your momentum changed very quickly. If your momentum changed very quickly, that implied that there must be a greater force on you, right? So for example, you can assume this diagram to be what? So let's say this was a ball that kept moving at the same momentum, let's say 5 momentum, okay? And it kept going from T1 to T2 with the same momentum. But what happened at T2? Let's say that you push the ball even with a greater force at T2. Then when you push the ball with a force, a resultant force, it obviously increased in its momentum, okay? And once you let go of the force, okay, what happened then? Then you now have a higher momentum, and then because now there's no resultant force, it's just going to keep on continue at a higher momentum, okay? But let's say, what if you came from the front? 1 second. Okay. Yes, there was some guy who was trying to scam me from my banking account, and I kept roasting the guy. Brother was clueless of what to say. Okay. So, what were we doing? Yes. Yes, the ball. If you have a resultant force, obviously the resultant force is going to change its momentum, right? You push a box, it's going to now gain a higher momentum. And because of the higher momentum, it's going to keep on continuing at the greater momentum. But let's say, what if you applied and force in the negative direction, or you, let's say the ball kept rolling like this, okay, but let's say you came from the front and you pushed it in this direction, that would obviously reduce its momentum. So that means you would now have a reduced momentum, and then it's going to continue like this. Okay, so that's basically just what's happening. It will be more apparent when we solve a few more questions. Okay, one other very important uh, one other very important statement, that if you had a force time graph, okay, so force time graph, if you had a force time graph, then you could basically use this graph to make this graph. How? So first of all, let's have this as T1, and that was T2 as in our previous example. That was T2, and that was T3. Okay, and so on. Okay. So first of all, you know that the slope of this graph is the force, which means that from T1 to T2, what is the slope? That means if the slope is 0, that means the resultant force is 0. So from T1 to T2, this graph is going to have a 0 line. Okay. Then you see that from T2 to T3, it has a constant resultant force. That means from T2 to T3, there was a constant resultant force like this. A constant resultant force like this, where the height of this is going to be FR, like this. Yep. So this is going to be the FR. FR. This is also the slope. Like, for example, if the slope came out to be 6, okay, if the slope came out to be 6 over here, then this would be 6 over here, 6 newtons. So that means from T2 to T3, a 6 Newton force was constantly being applied. Okay. But then what happens from T3 onwards? From T3 onwards, the slope is again 0. Slope is 0 from here to here. That means the resultant force is 0 again. So that means the graph continues like this again. Okay. Now, another really important piece of information for this graph. This graph is, these two graphs are going to tell you absolutely everything about the motion of something. Now, if FR is equals to delta P over delta T, doesn't that mean if you were to multiply FR into delta T, it's going to give you delta P, right? So that means if you were to take the area under the graph is equal to impulse. And what is impulse? That's just change in momentum. Impulse is change in momentum. Remember that. Impulse is change in momentum. Impulse is change in momentum. So that means if you were to take the area under the graph of this, this triangle or this rectangle, that's going to give you impulse, right? Why? Why is it going to give you change in momentum? Because you know that if you multiply resultant force with time, right? What is the length into width? This is the length, this is the width. If you multiply that, if you multiply force into time, it's going to give you change in momentum. This is impulse. So that's how you can go back and forth. So like if you take the area under the graph for this rectangle, it's going to give you this change in momentum. So it's like a very weird loop that you can get this from this, and then you can get this from this. This is only applicable. This is only, you could say, you could only understand this if you were actually to apply this in questions. It might not make sense right now, but we will do questions and it will make sense. Take like a, in fact, write this down right now. Try to absorb it in 2 minutes, and then we'll solve questions for this. Don't worry. When you solve questions, it'll be really apparent how to do it with values. Take a few minutes to absorb this. Write it down first Like take a separate sheet of paper, write it down. What is the slope? What does the area under the graph give me? And then we'll solve the question. So area under the graph of, so I'll write down the summary. Slope. Oh wait, let's just write momentum time. Momentum time M is equal to FR, and force time area under the graph is equal to delta P. Okay. And if you have any questions, you can let me know right now as well. Yes, guys, any questions for this? Anything that does not make sense? It's okay to be confused. What the hell is this? What the hell is this? It all connects together. It's like a thread. The thread is connecting everything. It's a woven into it. And every piece you pick out, every thread you pick out, they're all connected. Yes, Arez. Any
Yeah.
questions?
No.
No, have you done this before? This stuff?
I
Or no?
mean, I can understand it, though I think I should write it down.
You should. Yes, yes, you should absolutely do. When you solve, when you do it with numbers, where we have like momentum time graphs and we're going to plot the force time graph, it'll be even more apparent. But do write this down because we will use this in the next questions. We're going to take the concept of momentum time graph, slope, and the area under the graph and then apply it into questions. Yes, Hania, does this ring a bell?
No, I'm kind of confused how the graph
Hmm.
went from being like a straight sloping line. So like how is it
Hmm.
like a square
Hmm.
over there in the other graph?
Okay. Okay. So first of all, did you get this part where the slope of this graph is the resultant force, right?
Yeah.
The slope y, because delta p over delta t is resultant force. So doesn't a straight line have a constant gradient, which is, let's say example, this is 5. The slope came out to be 5. Now we know that this is 5 Newton, right? How much time was this 5 Newton force applied? Let's say it was applied from 2 seconds to 5 seconds. So the 5 Newton force was applied from 2 seconds to 5 seconds. So 5 Newton was applied for 3 total seconds, right? Did you get up? Did you get it up to this point?
Yeah.
Constant force of 5 Newton was applied from here to here. Now, if you were to see what's happening on the force time graph, okay, from T1 to T2, there was no force. So it would just stay 0, okay? Then you see from 2 seconds to 5 seconds, there was a constant force of 5 Newton. So that means there was a constant force of 5 newtons from T2 to T3. You can even like forget this. You can forget these upward sloping lines. This one. Oh, this one. There was a constant force of 5 newton for from T2 to T3. Okay, so you can like forget these bars. These were just for you to guide that what is the shape going to be, right? So from T1 to T2, there was 0 newtons of force. Then because of the slope of this curve, right? Because the slope of this line, there was a constant force from T2 to T3, which means that the graph of the force time is going to have a positive value from T2 to T3, right? So that's why you have an upward, you could say horizontal line, because there was a constant force of 5 newtons from T2 to T3. So that's why you had a horizontal line over here. Okay, now when you solve questions, you will see even better how you got that. Okay, does that clear it out a little bit?
Yeah.
It is directly related to this line. If this line, so basically, this line is this line. That's it. So if this slope is 5, then this line is also 5. If this slope was 10, then this line would be 10 over here. Okay. And for example, if the slope was negative, then you would have you could say a downward sloping force. Okay. Okay. Now I'm going to move on to the question and it'll make sense. Don't worry. So let's check it out. You have here a momentum time graph. Okay. Now the momentum time graph shows what? Initially the ball, let's say, was moving at a momentum of 10. Okay. Then what we saw was it changed. It changed from 10 to -8. Okay. Now we know that the slope of momentum time graph is what? It's equal to resultant force. Okay. So can we calculate the resultant force of this line? Right? Obviously, why is there a change in momentum? You see that the momentum changed from 10 to -8. There was a change in momentum because there must be a resultant force. The ball just kept moving at 10, momentum. Why did it switch to -8? Because someone might have pushed it in the other direction, right? How long did that person push the ball? This long, right? This whatever time that was. Okay. So how do we find out the change in momentum? Or let's find out the slope. Let's take this point and let's take this point. Can we calculate the slope of this? Right? Change in y over change in x. So y2 minus y1 over x2 minus x1. What is y2 minus y1? So this is 10 minus -8. Minus -8. Make sure you use the signs correctly. Divide by x2 minus x1. What is x2 minus x1? So that's what? That's 2 minus 6. Slope turns out to be what? 18 divided by 8. Okay. 18 divided by, no wait. 18 divided by
Should
-4.
be 18 divided by -4.
-4. Yes. 18 divided by -4. Okay. Okay. You're right. Now, in fact, wait, you know what? Let me make this a bit. Let's not get a fraction. Changing it a little bit so we don't get a fraction. Okay. Now, in this case, now it's actually 10 minus 10, right? And this is just going to be 20, right? So 20 minus 4, slope is going to be what? -5. That means that from here to here, from A to B, the slope is equal to -5. That means from A to B, or you could say from 2 seconds, t is equals to 2 to t is equals to 6. There was a constant force of 5 Newton or -5 Newton, right? Because the slope is negative. Okay. So that means that when the ball was moving initially at a momentum of 10, right? Then what happened was that there was probably a 5 Newton force in the negative direction, which stopped your ball to 0 momentum, and then it switched its direction to having a negative 10 momentum. So that means the ball has now switched direction to the negative side, right? So from A to B, the constant force was being applied, which changed your momentum from 10 to negative 10. Now, how do I plot the momentum time graph for this? Okay. So wait, how many seconds this? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. How do I plot the force time graph for this? First of all, was there any force in the first 2 seconds? Yes, Hania. Was there any force in the first 2 seconds? How do I know if there was any force?
There wasn't, because like it's the
Slope is
line.
0.
Like, yeah.
Exactly. So that means over here, I just draw a flat line, right? So this is 0 Newton. So for the first 2 seconds, there was 0 Newtons of force. There was no force on the object. Okay. Now, Ariz, was there any force from A to B? So from like 2 seconds to 6 seconds, was there any force?
Yes.
Yes. And we figured it out by calculating the slope. There was a negative 5 Newton force. So that means -1, -2, -3, -4, -5. So that means from 2 seconds to 6 seconds, there was a constant force. There was a constant force, right? So like up from here to here, there was a constant force of -5 Newton. Okay, then what happened? From B, okay, from B, what happened after B? Was there any force after B? From 6 seconds to 10 seconds. There was no force. Why? Because slope is 0, which means the resultant force is 0. So that means again, you continue from 6 seconds to 10 seconds, force is equals to 0. Force is equals to 0. And that's how you plot it. Okay. And by the way, one other thing, you can also confirm. I'll confirm it for you. The area under the graph for this one, area under the graph is equal to change in momentum. You can verify it. I guarantee it. What is the area under this graph? Let's check. Area under the graph is what? So 5 times 4. 5 times. So basically 5 times -4, right? Or -5 times 4 is equal to change in momentum. This is also what we call the impulse. Impulse. Change in momentum is just impulse. It's just another name. Okay. -20 is equal to change in momentum. So we verified it. We didn't need to do this, but let's verify. Was the change in momentum -20? Yes, it was. It was -20, no? It was -20. Or you can, think of it like this as well. That you went from 10, -10, and then -10. The change in momentum is -20. You have verified that. Okay. So that's how you connect them together. You have to be able to go from here to here and from here to here. It's a little bit daunting task. It's a little demanding. It's slightly weird, but you will get it. I will give you a few questions to solve related to this as well. Okay. Now, let's do another example. Okay. Again, very similar example. You've been given the momentum time graph. Okay. Initially, the ball had a -6 momentum time, and it kept staying at -6. Let's start plotting it side by side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm plotting the plotting the force time graph from momentum time graph. Now let's check. I see for the first like 5 seconds. Let's wait. For the first, how many seconds? For the first 4 seconds. For the first 4 seconds, there was no force, right? Because gradient is 0. Resultant force is 0 from 0 seconds to 4 seconds. So that means from 0 to 4 seconds, there was no force. So that means 0 Newton. Okay. Then what happened was that from 4 seconds to 6 seconds, there was a change in momentum. Change in momentum, right? That must mean there must be a resultant force acting for this sloped line. How do I calculate the resultant force on this area, on this line? Calculate the gradient. slope of this line is equal to what? It's change in y over change in x. What is the change in y? These 2 points. Let's take these 2 points. So what is the change in y? Y2 minus y1 over x2 minus x1. So 8 minus minus 6. And what is the change in x? So that's like 6 minus 4. That's what? 8, 2 is going to be 14 divided by 2. So 7 Newton is my resultant force. So that means that resultant force, this is going to imply a constant force of 7 Newton is being applied from 4 second to 6 second. Now, because this is what it means. This is what the slope is telling me. Okay. This means that from 4 seconds to 6 seconds, there was a positive 7 Newton force being applied. So that means, wait, oh, 1 second, 1, 2, 3, 4, 5, 6, 7, 2, 4, 6. Okay, wait. So let's just take the 2, 4, 6, 8, -2, -4, -6, -8. Okay. So that means that from 4 seconds to 6 seconds, there was a positive 7 Newton force that was being applied. So here to here. Okay. So 7 Newton. Okay. Then what? Then from 6 seconds to 10 seconds, slope was 0, which means the resultant force was 0. Then again, you continue with 0 force from 6 seconds to 10 seconds. So 0 force from 6 seconds to 10 seconds. And there you have it. Now again, let's verify. The the area under the graph is equal to impulse, change in momentum, impulse, right? Let's check. Can we verify that? Let's check. So what is the length? That's 4 multiplied by, sorry, no, that's 2 multiplied by 7, which is equals to 14. Is 14 the change in momentum? Let's check. So what? Is that 14? Yes, it is. 8 minus minus 6 is 14, right? So that's right. The change in momentum is 14. You can even like take this difference. Like what is this? So like 2, 4, 6, 8, 10, 12, 14. That's the change in momentum because that's what's on the y-axis. Okay. Any clarity, guys, so far?
Sir, I couldn't understand you. Could you just repeat? Sorry.
Which part? From where? From where
No,
point?
no, no,
Which point?
no, no. I didn't understand what you just said right now. Like your voice was glitching. That's it
Oh,
for me.
okay, okay. So what I was saying was, 1 second. What I was saying was that when you have, wait, what was I saying? What I was saying is, Aris, did you get up till this point how we plotted the force time graph?
Yeah,
You got how we got like how we plotted from this
yeah.
graph,
That
we
that
plotted
that.
this graph, right? Okay.
Yeah.
What I was saying at the end was that you can also verify that the area under the graph of a force time graph, area under the graph is going to give me change in momentum. Okay. Aris, do you know how
Okay.
we got this? How do we know that area under the graph is change in momentum? Do you remember? Because force multiplied by time is change in momentum. If you
Yeah.
remember, right? FR is what?
Yeah.
FR is delta P over delta T. If you
Yeah.
multiply it with time, that gives you delta P, right? So that means if you multiply
Yeah.
force with time, that's going to give you delta P. So that means
No,
we can
yeah.
verify. Now, what are you saying?
No,
Got
no,
it?
no. Yeah.
Okay. So that means if you take the area under the graph for this rectangle, rectangle, so 2 multiplied by what? 7 is 14. So 14 is my change in momentum. We can go back to our original graph and check. Is the change in momentum 14? Let's check. Isn't this the change in momentum? Right?
Yeah.
Change in momentum. This is what? 2, 4, 6, 8, 10, 12, 14. So 14 is clearly my change in momentum. So you've verified it from both sides. Okay. So you can go back and forth between these two. Okay. Yes, Hania, is it making sense?
Yeah, I get it better
Yes.
now.
Okay, great. Yes, Kaima, is it making sense what we're doing?
Yeah, but I'm a bit
Hmm.
confused. Sir, can I please send the recording later? I would
Hmm.
like to watch it
I will.
again.
I will. That's why I recorded it. Okay. This is slightly confusing. It is a little difficult if you don't write it on your own and try to make it on your own. Right now, I am the only one that, practicing in front of you. You will have to sit down after class and you will have to absorb it. There is no shortcut for A-level physics. A-level physics is challenging. I have done my best to show you everything, whatever there is, how they connect together. I've shown you multiple examples. We'll be doing more in the next class. And but you will have to put in the effort as well. I've shown you the way. I've shown you the cleanest way there is, the easiest way to understand it, the major principles that if you understand these principles, you will get the question. But you will have to put in some effort to put it inside your brain. Okay, and putting it inside your brain does not mean sleeping on your notes when you go to bed. Okay, try to active recall. Try to see that whatever I've written, why have I written it? Does it make sense? Does it connect together? Is there a mistake in my notes? Compare with your original notes. You can ask ChatGPT. You can ask me in the group. Okay, if you will not put in any effort, you will not get a good grade. Only I will. I already have my A levels, so like it's a win-win for you guys. You've got to study on your own. The most of the studying happens after class. Within the class, I'm only showing you stuff. I'm only exposing you to content. Okay, I have updated the note and I'll also send you the recording. Check it out. You will see that it makes sense. Okay, we'll be solving a few more questions in the next class. But before then, try to understand all of this. Just to like, I believe you did understand all of this stuff. But this one, you will have to draw it on your own. You'll have to like probably take out a graph paper and you will have to solve it and see whether they connect together. Okay, we've done 2 examples and we'll be doing more examples in the next class. Okay, sounds good. That's all what we'll be doing in the next class. Questions of this. So make sure you try to understand this. And if you even if you don't, make sure you have questions that I did not understand this part. Okay, excellent. Sounds good. Physics is tough, but don't worry. I've tried to make it as fun and understanding as possible. Understandable. Oh, okay. I will share the recording in